Okay, so
Hang on.
yeah.
Let me introduce you.
Yeah. Go ahead.
Right, so this is stage 3 assessment for Ahmed Al-Zubaydi. He's our PhD candidate supervised by Wong and Nikki, both here today. And his thesis is titled Design Modeling Experimental Evaluation of Energy Recovery for Indirect Evaporative Cooling System.
Too long.
Very.
Yeah.
Take it away.
Okay. So the contents of this introduction is going to be first the introduction, the research objective, research methodology, results, conclusion, list of application, and future work. So everybody like to see this photo. That's an ad from the 50s about the air conditioning system. Yeah, nice. You're going to have a happy life when the summer is coming. But what are the consequences for that? As you're going to cool any building, you're going to put money on that for the electricity. You're going to put exhaust air, and this will be generating for the CO and spending money. The 40% of the energy for the commercial buildings is actually spent on the HVAC system. That the chiller, the pumps, and the cooling towers. That's too much. We're talking about hundreds of thousands of megajoule per square meter. Now, the temperature is still increasing, and that's what will be the result. Hundreds of the air conditioning system to be used. What will happen? January 2019, we got something called the Victoria warning. The demand was much more than the supply. 929 megawatt gap. Now, the problem is that the temperature is still increasing. The weather in Europe, something like 45 degrees in Paris. This is the hottest summer in 125 years. No, this is the coolest summer in the next 125 years. And that's what we have to think about it. Now, the problem is about how we make the energy, how we make the electricity. The hydro, the wind power, and the solar renewable energy, everybody talking about that. But it's still in very low figures, not more than 10%. Everything's still depending on the fossil fuel. And this is one of the main reasons for the global warming. So what the future is, New South Wales by 2025, how much? 5% or less coming from the renewable energy? South Australia, because actually they don't have a lot of consumption, so they can depend on the renewable energy. That's good. But what about the other states? That's the demand for the air conditioning in the next 80 years. Now we are standing at this level, something around the 3 exajoules. That's good. Temperature is increasing. The technology is getting cheaper for the conventional system. The life standard is increasing, so everybody now is capable to buy air conditioning system. By 100 years, is going to increase by 50 times. That's disaster. Now, the HVAC system is like that. That's what we have in most of the buildings. We have fresh air to be mixed with the return air coming from the building, which is actually spoiled air. Others, the CO2, the other thing, and it's going to be mixed with the fresh air to pre-cool it to a certain level, then passing it through the cooling coil and the heating coil, send it to the zone. Take off the heat from the zone, send out as a return air. Portion of it usually is 50-50 or 30-70 is going to return back to the zone. So 70%, 50-70% is going to be exhaust air. That's mean we're losing energy for that. So simply we can put a heat exchanger. Utilize 100% of the air to pre-cool the fresh air. Heat exchanger, plate heat exchanger similar to that. Parallel channels, hot and dry. Hot and cold, or dry and wet in the inductor of the cooler. And we're going to have pre-cooling, and thus we're going to have cold air to be cooling further, and thus we're going to reduce the energy consumptions from the vapor compression system. Okay, now my research is about this point. If I'm going to make it 100% utilized air by the heat exchangers or the inductor of the cooler, we can save money for that. So usually we know that evaporative cooling is a natural way for the comfort cooling, environment friendly, no gases. Actually, the refrigerant is going to be this 118, which is the R718, which is the water. The direct adaptive cooling is usually going to add a humidity to the supplied air, and this is something undesirable. The indirect sensible cooling add no humidity, and this is the main advantage for both. No compressor, thus we are going to have lower energy usage for both. So this is a comparison between the two cases, and actually we should go for this one using the indirect cooler either as a 100% standard-free cooling system, because you know that the days in Australia so far, the temperature outside is quite good. There's only have to treat the air for a little bit lower and send it to the zone, and thus we don't need to use the compression, the vapor compression system in most of the cases. So these are the advantages of the indirect cooler: the sensible cooling, the using of plate heat exchanger, the adding of the can be added as a pre-cooler system and can be utilized as energy recovery ventilation system. We're going to have health advantage and financial advantage at the same time. So the concept is we're going to have parallel channels, wet and dry, that's in the indirect cooler, or hot and cold in the case of the heat recovery ventilation system. So as you can see that we are going to have the primary air, which is going to be the fresh air in this case, is going to run through the dry channel, do heat transfer with the plate wall. On the other side, the plate wall is going to have water layer. We're going to have the return air coming from the building, which is cold air actually, passing it through the water film, cool it down, and thus we're going to cool down the plate, and thus we're going to increase the heat transfer rate between the primary air before we're going to supply it to the zone. That's what the people like to see, the academics like to see, but not the engineers. That's what will happen actually in terms of the thermodynamics. The primary air is the hot air, the return air is the blue one, the cold one, water layer on the plate. Mass and heat transfer in the wet channel. The cold air is going to absorb the heat from the water, make it colder, thus the plate is going to be colder, and this will increase the sensible heat transfer between the primary air and the plate. In certain situations, if the humidity of the primary air is going to be high and the plate temperature is going to reach the dew point temperature of the primary air, we're going to have a condensation layer on the dry side. Sometimes, well actually most of the cases, because we're going to have a latent heat transfer, this will be a negative effect on the performance of the indirect cooler. This is just a sample of the research I went through the literature review, and actually I concentrate on the following: what the type of the inductive cooler you're using. Now you can see we have different types. We're going to talk about this one later. The heat exchanger position, the flow rate ratio between the primary and secondary air, the water to air flow direction, the primary air source and the secondary air source, and the methodology used in this study. So I'm going to tell you what I from that. In my study, I need to do the following. First, I'm going to use a horizontal spray. Now, this is my plate. Horizontal spray while the air is coming vertically. Vertical hexagonal quasi-flow plastic heat exchanger. Doing experimental tests on the IEC units. Do the uncertainty analysis for the results, and build a CFD model and do the simulation and validate it. Basically, my study got the idea from two research. Well, just imagine that only two research earlier done the work of the water distribution in the indirect cooler. The first one is done by Huang in 2010, and actually I couldn't get the work itself, but it was mentioned by the one in 2011 because this is a PhD thesis in Chinese, and I couldn't trace it. So I got the diagram from the one publication, cross-flow heat exchanger, and the secondary air is coming from below, the water is spraying from the outside. That's the traditional method for the water spraying in the indirect cooler. So he tried multi-level for the water spraying. He put it in the middle. Once again, it's going to be counter flow rate to the air. And then he put it to the bottom and tried to spray it on the same direction, parallel to the air flow rate for the secondary air. The other work is by the Antilles in 2016. He just changed the direction of the nozzles. It's either going to spray the water parallel to the direction of the water to the secondary air at the entrance of the heat exchanger, or he made it a counter flow to the air direction. Actually, he got a good result by making the water going cross flow to the air direction, because a pre-cooling process has been done before entering the heat exchanger and doing the heat transfer within the channels. So I thought about this system. Internal micro nozzles inside the heat exchanger plate, which is 6 millimeter thickness only. So this is one of the dilemma I faced on how to make the nozzles inside the heat exchanger channel. That's the traditional method, having the external sprayers. And these are the internal sprayers. The blue is the wet channel. The red is the dry channel. And we're going to test that experimentally and using the CA3 system. So how to get the micro nozzles inside? So I was thinking about something, many methods. And I was walking in the street, I saw that. So I did the same. I got 4 millimeter diameter tube, punctured with the needle, tested outside. This was giving me the results I would like to have, implemented inside the heat exchanger. For the external sprayer, we have many of those sprayers, high pressure sprayer, which can generate the mist. So mainly what I would like to have is check what the plate surface geometry affects on the heat recovery ventilation system. A dry system, no water spraying, cold air and hot air from the other side. Check what will be the surface geometry effect on the heat exchanger performance. The other one is checking what will be the water spraying mode effect on the IEC performance by using the 3 different methods. The classical method with the external sprayer mode, the internal sprayer mode suggested by inserting the tube inside the heat exchanger, and making the mixed mode. Both are going to work at the same time. So the objective was building the test facility. Flexible, which can be used for testing the HRV and the IEC system, or any system which using the counter flow heat exchangers. Design and build the heat exchanger themselves, including the implementing of the tube inside. Well, actually, as I told you, it was meant to be a nozzles, and I changed it to the tube. Then do experimental test for testing both systems, changing the input parameters, which can be shown in the next step, and develop a CFD model, 3-dimensional. And this is actually, beside the water spraying system novelty, this is very novel because this is the first model which is in 3-dimension with a realistic sprayers within. Usually they just consider that the water is covering the whole plate and do the simulation for that. In my case, I made a realistic, I simulated the nozzles within the heat exchanger channel. So the methodology, once again, is going to be first preparing everything, mathematical model and building the test rig, do the experimental investigation for the test rig, and do mathematical CFD model on the other side, get the result, make the analysis, CFD model validation, do a basic energy auditing analysis, and get the conclusion. So for objective number 1, the test facility must be standardized. Otherwise, we cannot say that this is going to be accurate results. So I took 2 standards. The first one is for testing the air-to-air heat exchangers for energy recovery ventilation equipments. And the other one is for the testing of the indirect level coolers. Both are American standards, but they are actually the only standards we have for both testing. So this is the original schematic diagram for the test rig. I made my own module because actually it's the flexibility to add or remove something. So I just made it as an open loop test facility. Secondary inlet, primary inlet to be simply modified before we're going to send it to the test module. And we have 4 testing stations for the measurements of the parameters. So we end up with 2 schematic test rigs, one for the HRV system and the other one for the indirect cooler. The only difference is going to be the presence of the water cycle in the case of the indirect cooler. So what we have is we treated the outside air to take it to a certain temperature. The secondary air is going to be the room temperature, which is at summertime something about 22 to 24 degrees at the UTS. So we consider this one is the return air and this one is the outlet air. Design and manufacturing of the test rig, all done by myself. Finish the thing, put all the measurement equipment, the 4 stations, 1, 2, 3, 4, as you saw in the previous schematic diagram, connected to a system where we can simply modify the air temperature and humidity to a certain level. The water pump is sitting here somewhere in the back, the 2 fans. As you can see, this will be the return air entry going through the heat exchanger, and this is the exhaust air, red color. The hot air, which been made up by the machine, is going to be passing it through the dry channel, and we're going to have the supply air. Data loggers everywhere, sensors everywhere, and to have more accuracy, I use the primary and secondary measurement stations. Just to double check if the readings are going to be correct, I made my own air sampler. Again, to have the fan, multiple holes, take the samples of the air stream, mix it, dry bulb temperature and wet bulb temperature measurement, calibrated. So to connect it to make up the air, I use the unit we installed for air conditioning subject, the A660, with modification because usually it's have a digital changing for the temperature. I made it more incremental by using the variable resistance. So we supplied the air. This one is the outside air to the test rig. The room temperature is secondary air, and we have 2 exits, and the station is already being shown in this diagram. Objective number 2 is building the heat exchangers prototypes. So this is the concept of the quasi-flow heat exchanger. Quasi-flow, that means we're going to have cross-flow and counter-flow. Because it's almost impossible to have a pure counter-flow heat exchanger. I will work on making it as much as possible counter-flow heat exchanger in the future. So what we try to do usually is to increase this distance to have pure counter-flow, at least in this point. So that's what happened. The red is going to be for the dry channel. The red is for the wet channel, and we start to build the things. So at the first part, the HRV system, as we mentioned earlier, we're going to have 2 different surfaces, the dimpled one and the flat surface. Of course, the other one is going to consider to be a high turbulence surface. The other one is laminar flow surface. We made the mold, we did the thermoforming for the faces, we built the heat exchanger. The heat exchangers have something about 72 channels in total. Okay, this is the other heat exchanger, which is for the indirect cooler. I did the whole thing to have the 72 channels. That's only for the case of the HRV. But for the IEC, I just made it at 48 or almost 48 channels for the test, because actually I didn't want to connect the tube for longer, so I just stopped at this stage. So this indicates what the location of the spray position. Simply it has been fixed, then function in position. I tested earlier outside and this gave me the results required, and I tested at each stage until I finished the work. Actually, I spent the Christmas holiday doing that. I was alone working at level 10 at the UTS, me and the security. So these are the stages of building the things, preparing all the heat exchanger plates, stuck the thing on top of each other, fixing the tube inside the heat exchanger channel so the thing is going to move due to the pressure of the water. I added the extended ducts for more accuracy for the water spraying and the measurement. Sorry?
How many plates are there?
For this one? Totally 72, but for the wet channel it's only 48. So we did the calibration and commissioning for the system, spraying the water. This is the external one, so obviously you can see that the water didn't cover everything. Oh no, I think this one have the internal one, and that's why we got the wetted thing. So objective 3A, I call it 3A because it's for the HRV. The evaluation parameters were the sensible efficiency, the cooling capacity, and the coefficient of performance. So the parameters variation was mainly about the inlet primary air temperature, the inlet primary air humidity, the inlet primary air velocity, the inlet secondary air temperature, the inlet secondary air humidity, and the inlet secondary air velocity. So before we are going to check that the system, before we take the measurements, we have to check if the system is balanced and heat transfer on both channels. So we take many experimental readings, and we found that the variation is actually within the limits of 10% error. And this is usually acceptable depending on the references I use for similar studies. Accordingly, when I show that I have the energy balance, the energy balance, that means the heat transfer in the primary air is going to be equal to the heat transfer on the secondary air. This is almost an ideal case, but when we got just 10% error, that's been within the limit. So the first experiment was checking the effect of the primary air temperature on the performance of the HRV system. The red one is the flat plate, and the black one is the dimple face. So definitely it's give you 50% improvement by checking the changing the surface. Now that's good, but it's not very good. Mainly because we are going to have pressure drop due to the turbulences inside the heat exchanger. So good improvement in the terms of the efficiency, in terms of the heat transfer rate, which is we call the cooling capacity, and of course with the COP value. Now the playing with the air velocity and check what the effects of the air velocity. Now, as I'm going to increase the velocity of the primary air, the efficiency of the heat exchangers both are going to be dropped down. Still, the heat exchanger 2 is working better than the heat exchanger 1. While if I'm going to increase the secondary air velocity, I'm going to have a good performance for both. Now, the explanation of that, I'm going to keep it for the discussion. You asked me about this point in the discussion. So the other parameters is going to be the QB, the cooling capacity, and the cooling capacity when changing the velocity of the secondary air. Now we saw that the efficiency actually is dropping down, but the cooling capacity is increasing. Cooling capacity increasing, but the COP is decreasing for both. This will make you wonder, simply because when I'm going to increase the velocity, I'm increasing mass flow rate. That's why the heat exchange, the heat transfer rate has been increased. And because each time I'm increasing the velocity of the fan, more power is going to be used by the fan, and thus the COP value will be declined. The third, objective 3B is the DC prototype. So the parameters now is going to be changed. We don't use the sensible efficiency, we're using the wet bulb efficiency, because we are going to use the wet bulb temperature, which is in this experiment is going to be approximately standard. It's not going to be vary. And checking what will be the efficiency of the IEC units. Sensible cooling capacity, because only the sensible heat will be transferred through the plate. The coefficient of performance, and we added later the water evaporation rate. The result for all these three has been already published, but for this part, hadn't published yet because I added after we did the submission of the publication. Now, this point is very important because the water is a precious item. So each time we working on something evaporating the water, we're going to lose some water. So we have to make this sensitivity test. So the input actually is going to be almost the same, but we just added these two parameters, which is the water mass flow rate and the water temperature. This is not actually a control thing. That's because the water as evaporating is losing temperature. And then we have to add up water to the sump to replace the evaporated water. Once again, we do the energy balancing, and they're still within the same range for the three modes of the water spraying. So the first one, well, I added a new term, which is the delta TB, or the primary air temperature depression. So you can see that now this is a classical method, external sprayer. The internal sprayer has simply modified the performance of the system, and having the mixed mode can cool down the air by 14 centigrade if I can send it at the temperature of 36.8 degree, performing better when the temperature is going to be higher, simply once again because the delta T across the plate is going to be higher, the constant secondary air temperature. Obviously, the efficiency of the watt valve is going to be increasing. The Q sensible is going to be increasing. Just imagine that we got 1,760 watt cooling capacity, half ton, for 24 wet channels only. Again, to expand this one to a higher rate, then we can get the same cooling rate of a small substitute unit with 200 watts. Okay, and this is COB value because actually we didn't had too much power because the flow is laminar in the heat exchanger. Delta TB with the velocity changes. Now, once again, we are going to have the same problem. The system performance is going to decline as I'm going to increase the velocity of the primary air. And this is for the secondary air velocity, the efficiency, the primary air velocity, the efficiency will drop down accordingly. And the Q is going to increase for the same reason, the mass flow rate is increased, and the COP is going to increase because, as I mentioned once again, the power consumption in the laminar flow is not going to be too high. For the secondary air velocity increasing is going to increase the efficiency of the heat exchanger in the IEC modes because we are going to increase the evaporation rate on the water layer. The capacity of the cooling will increase and the COP has increased as well. Now, the effects of the moisture air content. And this is very sensitive point, especially in Australia and the tropical countries. Usually, when you're going to have higher humidity, the advantages of the IEC unit is going to be lower. So what's happening is that because we have high humidity ratio in the primary air, the condensation and latent heat appear, and this causes a negative effect on the IEC performance. And this is for the cooling effect. Once again, is going down because some of the heat transfer has been changed into latent heat. So actually, if I'm going to calculate, the total Q is going to go up. So each time I increase the humidity, I'm going to have QL higher than the to be increased, and thus reducing the Q sensible. Now, the water evaporation rate, I just checked the effects of the temperature of the primary air on the water evaporation rate, and actually I can see that the limits of 1.15 liter per hour is within the acceptable limits. So I'll jump to the CFD modeling and validation. So I use the Lagrangian approach. I use the Rand's conservation equations, the K epsilon turbulence model, the DPM for the water droplet, and the two-way coupling to couple the approaches for both the evaporation and the dry air. So I just took the sample, one dry channel in between two wet channels, putting the ducts the same as in the real life. This is the boundary layer for the fluid domain. The plates are going to be separating the fluid domains in the wet and dry channel. I did the mesh independent test and sensitivity analysis. I found that the best result is going to be obtained if we're going to have 2.5 million elements with 1 million nodes count. If I'm going to reduce the size of the grid, it's not going to give me any significant effects on the simulation result. So once again, this is a novelty of the work, more realistic mode by simply inserting the water spraying within the heat exchanger. And that's what we got. Water distribution in the wet channel was improved. I just visualized the thing. Actually, I tried to do the same thing with the experimental work. I searched a lot for the thermal camera. Nobody told me where can I find it. Anyway, this is the external sprayer. Internal sprayer. The red means more water in this point. The mixed mode. Actually, that's it. The constant has been improved. We can see that we did the main thing, which is the increasing of the wettability of the wet channel. So that's what's happening in the terms of the temperature in the wet channel. So this is the HRV. We just put 296 Kelvin, no water spraying. This will be the temperature distribution. Turn on the external sprayer. This can take the temperature down to something about the blue one, 292. The internal sprayer can take it further in some region to 291. All sprayer mode can take the temperature outside to 290 because the water evaporation starts to appear. And this goes down further. So what will happen on the other side in the dry channel? Okay, so water distribution in the wet channel has been improved, and that's the most important thing. For the HRV, we're going to have the cooling rate of the dry channel air is going to be extended to the last quarter of the heat exchanger area. We improve it with the external mode, further with the internal mode, and a lot with the mixed mode. So that's just visualization of the things. I didn't explain that yet in my work, but I think that this section is going to be a chapter by, it can be a publication by itself. So the concept of the primary air cooling rate in the dry channel has been improved. So I did just simulation by changing the parameters for the air and the water droplet parameters, and I got some results. First, I have to make a comparison between the experimental and the simulation outputs for the primary air supply temperature. So actually, I can see that the precision is going to be within this range. I said it's going to be in 7%, but actually it's going to be in 3.5% only. Approve the things, try to repeat the same experimental work. Changing the primary air temperature, same thing has been happened. The supply air temperature has been increasing, and the wet bulb efficiencies has been increasing, and relative humidity will go down. Now, this is relative humidity. This is not the moisture content. So obviously, if the temperature is going to increase, RH value is going to decrease. Now, for the changing of the primary air velocity, now the temperature is simply going to increase. We approve that experimentally. The relative humidity will decrease, and the wet bulb effectiveness will be decreasing. In the third case, which is the humidity ratio, the only thing which is going to be increased is the temperature. Relative humidity now, because the moisture content is going to be higher at higher temperature, so that's why it's going to be increasing, while the wet bulb efficiency will be decreasing because the delta B for the primary air is going to be increasing. So in conclusion, the experimental facility has been built and commissioned based on the ASHRAE standards. Indirect cooling using the quasi-contour flow heat exchanger code was experimentally tested with the 3 water spraying modes, including the novel internal spraying system. The test showed that the internal modes improved the efficiency by 3.5 to 5.2%. The cooling capacity by 12.5% compared to the classical external spraying mode. For the internal spraying mode experiment is substantiated to the effective methods to increase the IEC utilizing of the hexagonal plate heat exchangers, mainly by the means of the increasing of the wet surface area has been improved. The mixed mode, which is both systems, can give you the cooling capacity of half refrigeration ton with the efficiency of 76%. The CFD model was built and validated against experimental results. The CFD simulation helped to visualize the mass and heat transfer in the IEC unit in the 3 operation modes. The effects of the plate surface with the HRV unit was experimentally tested, and the comparison between the two heat exchangers, the dimpled face and the flat face plates was done, and the test showed that the dimpled surface increased the HRV efficiency by 20% over the flat surface in general, 50% in the case of increasing the temperature, but in general it was 20% better. The high turbulence resulted in the high performance in the dimpled face pattern. However, the cause of the higher pressure drop and the fan consumptions were these two disadvantages. So for the future work, again, to expand the CFD simulation parameters to include the geometry of the heat exchanger. But the only problem I'm going to have, I would not be able to take the gap between the plates less than 6 millimeters because the sprayer will not going to work in this case. Investigate more water spraying arrangements. I have multiple ideas created during the study. Improve the quantity flow counter heat exchanger to minimize the cross flow area and maximize the counter flow path. Then design and commission a domestic size IEC unit, something you can use it instead of the portable vapor compression system. If you are going to have this one in-house, working very nice, then drop the cost of the electricity by using a system which is using few hundreds of watts instead of 500 to 600.
To sell.
Yeah, to sell. Yeah. We are partner in that. Okay. One of the future work, I have to go to the gym to drop my belly. The publication are 3. First one was the conference in Brisbane. We have 2 citations for that. Another publication by me and Guang in 2018. That's before you came. 3 publications so far. Well, I know it's published in December. So anyway, the latest one published by February or March is mainly about the experimental work of the IEC system. Acknowledgement. I got the research training program scholarship, and actually I would like to thank every one of you. You were a good supporter all the time and good friends. Thank you very much. That's not me, that's any engineer trying to save the world. So any questions?
Questions?
I was too fast.
How about your thesis?
I'm working on that. I got more feedback from him yesterday. Yes.
So I'm going to spend the weekend going through the rest of the chapters. But your figures
Which figure?
Around the 30s, why are all the fit lines quadratic? The data looks pretty linear.
No, they're not.
Yeah.
Oh, if you talk about the CFD, yes. That's what we are going to get because it doesn't actually.
Not the CFD.
The expand work.
Like figure 30s.
Yeah. They're not linear, but I try to fit it as linear.
So the equations down there are quadratic.
This one.
Yeah.
Well, that's for the fitting, not for the results.
Yeah, but they look linear. Like, why did you choose a quadratic fit?
Depending on the R value I got for the linear fitting. I got the higher R value. I know this is not the real case. Yeah. Usually the R9.99 doesn't mean it's better than the R97, but that's what I use in this diagram.
Yeah. Let's change those to linear.
Okay.
Because wouldn't you also usually do a thing based on?
Yeah, that's my suggestion as well.
Which one?
All of them linear. You remember I said.
Yeah.
Yeah, and they don't mix the linear and the non-linear.
Unless there's some reason to think that the dependency is quadratic, start with linear.
Yeah, you'd want to base it on what the physical relationship is between the 2 quantities.
Yeah.
Say to start there, and if not,
But the purpose is not for fitting. It's
No.
to derive
Exactly.
the mathematical models.
Yeah.
So if they are consistent or linear, it would be better. I think the curve one actually the R would be very small.
Yeah. Well, actually, as I told you, I just tried to find the best R, but I know that's wrong because usually best R doesn't mean it's a good fitting. But that Yeah, but that's what the people like to see.
Yeah, seventh order polynomial.
Okay. Which one we meant to talk about? Yeah, we're increasing the velocity. What's happened? This one. Now, actually, what's happened? Why when I increase the primary air velocity, the declining will happen. While when I decrease the secondary air velocity, the performance will be better. Usually, what's happened here that the air will pass the plate faster. So we're going to have enough time for the effective heat exchange. That's the reason for that. But though the Q has been increased because the mass flow rate in the equation has been increased.
No, I think it's very good. Just random questions. How did you get the dimple size?
Oh, well, from brain.
Okay.
Yeah, because actually what's happened now, let's talk about this one. Why we had this experiment at the first place.
Yeah, following the dimple one,
yes.
Go to the conclusions?
Yeah, we can. Yeah. Following? Okay, let's talk about the dimple phase.
Yeah. Let's talk about the dimple first.
Okay, now what's happening is that at the beginning, John Donald was the course supervisor. And he suggested just to make the test on different shape for the geometry. So I made a dimple phase. Actually, it was corrugated phase at the beginning, and I had a publication for that. But later he said, no, this is breaking my IP. So I changed the thing from the corrugated to the dimple phase. Okay. How did I got the idea? Now, once again, something similar to the tube with the holes. I opened the drawer. My wife is a pharmacist. She had a lot of medicine there. So I saw the sheet for the medicine for the dimple phase. So I thought this is the phase I'm going to make, but with some changes. Because going on both sides and alternatively.
Because my thought is the next logical thing would be to test the height of those and the distribution of them.
Yeah, we can do that. Yeah. This can go with the future work. Now let's go to one.
Have you finished?
Yeah. Which point?
Yeah, the 7.
7. Yes.
Just the conclusions we want to conclude the most significant achievements.
Yeah.
Right? Yeah. Number 7, if without any experiments, do you think we know that?
If I'm going to make the right. You're right. Yeah. No, actually, I did the measurements for that. You remember?
Yeah. Then you present your results quantitatively. How much will be affected?
Yeah.
That will make the conclusion.
Yeah. That's shown actually in chapter number 3 in the thesis for the pretest. I did the pretest for both. Okay. Yeah. Okay. I thought it's a pretest operation, so it doesn't have to be shown here.
Or if you conclude like that, then the readers think, oh, without any research, we know that. Yeah. But quantitative, how much the effect, the actual effect, you investigate it and conclude. Yeah. So
you remember we put that in this publication, and it's already there on the thesis. But anyway, again, to try to put it on any next presentation.
That's I didn't mean any problem with your results.
No.
And also still the objectives, actually they are still tasks. They are very nice tasks, but they are not objectives.
Okay.
Yeah, then that's
we've been discussing about that for 4.5 years.
Can I ask you about you showed your experiments and your simulation data and the comparison, you put the 7% error, but maybe we can have a look at that graph. Yeah. So in general, let me see, the experimental ones are slightly higher. Do you have a feeling for why that is? So they tend to be above the black line in the middle.
No, most of them are going to be the same. Yeah, this is a 45 degree. And these are the results I'm going to show you in the table when I listed everything. That's what need all the table. So actually, when we're going to talk about the indirect cooler in the real life, this is a very complicated operation because we are going to have wet channel, multiple sprays, the evaporation happening. We assume that the case in the experimental work is fully insulated, but it's not. But when we say it's fully insulated in the case of the simulation, it will. That's what made this changes in the reading. Yeah, the simulation is the ideal case, but the real life is anything but not ideal case.
Yeah, usually this is plotted the other way, right? So simulation is predicting higher values than the experiment is achieving. Is that right?
I think that's consistently higher.
Yeah.
Consistent high.
Yeah. Now, one of the things which causes this diagram to occur is that the water temperature, right?
Yeah.
Because the water temperature just keep decreasing, keep decreasing all the time when I do the washing.
That's like I said. So you gave a range of like 19 to 22 degrees. Does that mean you?
That's what I measured.
Okay, so but it varies across that.
Anything between that, yeah. Okay. So when I do the CFD, I have to set it as constant.
Yeah, sure.
But in real life, it's changing. It just keep changing between this range.
I think that he can adjust move a little bit down in the simulation. I'm sure. Yeah.
And one other thing you mentioned was something about you gave your evaporation rates, and I think your highest one was about 1.5 kilos an hour or something like that.
1.18.
Yeah, but you said something like that's within an acceptable range. So I just wondered, what does that mean? How do you know what an acceptable
compared to the other studies?
Okay. Compared to other studies, but what about compared to? Because you mentioned you're going to build one of these.
Yeah.
Is that an acceptable range if someone was to put these in their house?
Well, let's talk about what's available in real life. The small evaporative cooler, and actually I checked that myself. It's too small. The cooling capacity is too small, and still send more humidity to the room, and it's consuming something about in the hot days, something between 2 to 2.5 liters per 1 hour.
Okay.
So by having better cooling efficiency, better cooling rate, with 1.15 with the mix, it's great.
Yeah, that sounds good.
Yeah, but actually next study, the one I told you about, we're going to work on together. I'm not going to use any of these sprayers. I have a different method for the water distribution.
Do you have statistical variation in these data points? Is there errors that are hidden?
Oh, for the error. Yeah, I did the uncertainty analysis, statistical, and it's available in the, what chapter? In I forgot, chapter 4 and 5, I think. And it's already there. Yeah, and the experimental work.
But it's still good. If you can
Yeah.
yeah.
I did the uncertainty analysis not only for the, these are the average actually, when I did it for 5 minutes, and then averaging the value, put it here. But yeah, because it's just keep changing every 10 seconds, so it's not going to be constant. It will go up and down a little bit. But in all the cases, these are average value. But for the whole readings, I have done the uncertainty analysis using the statistical method.
It's just good to include error bars on these if you have.
It's going to be too big.
If it's too busy.
Yeah, I tried to check to try to make it smaller. I couldn't make it. If you help me with that, this would be great.
We'll have a look at it. Because if it makes the plots too messy, then we'll just put it in a table.
Yeah. Okay.
You could just have it in the figure capture.
Yeah, we just have what the error is.
Did you tell everyone what's this for? Did you mention about the exhaust gas air?
Yeah.
Oh, you did. Oh, at the beginning, I just missed it because we forgot this in the abstract.
Yeah.
All of this is for using the wasted energy from the exhaust air.
Yeah, it was shown in these two diagrams.
Yeah,
that's
I like
all right.
I liked how early
I just
it was.
make sure.
This.
That's the important part.
One final question then. You mentioned that you did the 3D CFD, and you sort of said that most people do 2D.
No, I didn't say they 2D. I think there are Chiao in 2016, he did 3D. Okay. And another guy, I think his name is Bakar, 2019, he did the 3D. So but the problem with that.
Yeah, it wasn't so much that. I wasn't.
Yeah.
But it was more to what did that 3D give you? Because obviously it was more complicated and more difficult to do, right? But
yeah.
What did you gain from doing that as opposed to 2D?
A real life elasticity. Because what's happening usually they consider that okay, now this plate is wetted 100%. Then they do the simulation. In my case, I put the nozzles. So it's actually simulating the real life case. Nozzles spraying the water. No, I didn't compare that because their system is quite different. It's something like this one. This is another type of the inductive cooler. The one we're using can be used for energy recovery ventilation. This one is not, because this one is going to have one inlet It's either going to be the outside air or the inside air, but not both. And the same air is going to be simply divided into two streams. One of them is going to go and return back and go out from this side, and the other one is going to be supplied to the room. So their system was similar to that. So I couldn't simply validate my system against them.
Yeah, I mean,
but I will try.
It clearly showed that was the assumption the 2D would make wouldn't work as well as what you did.
Yeah.
So I think it's
yeah, it's impossible. Yeah.
You mentioned 2.5 million elements or nodes.
Oh yeah.
Were you having convergence issues?
Well, if I get to less is going to make the conversion, but usually the higher never. But it's going to be too slow.
Yeah. So, did you run into challenges with the numerical model conversion?
Yeah, I did this. Well, something about. I didn't show that in the thesis, by the way, but I did this study, the sensitivity study. I tried to certain amount each time again to make it finer until again to got this value, the 2.5 million.
Yeah. Okay. So you did some sort of convergence
Yes.
study to make sure that 2.5 is a.
Yeah. Otherwise, it's not going to be acceptable. Yeah.
Cool.
But once again, I didn't this study within the thesis because I tried to make it shorter.
Let's put it in the appendix. Just
okay.
One of your assessors or thesis.
You got me one expert in the CFD.
Yeah.
Thank you very much.
He's gonna look for it.
Okay.
And you have done very good, excellent jobs. I think you should present well.
Thank you very much.
Show the best. That's what I think. You know. Yeah. To the examiners.
Hopefully, I will do. Okay.
Right. Yeah. That's it. Anyone else? Alright, we'll wrap it up. We'll get time to leave the room and the panel will discuss.
Thank you.